last 5 problems from 2013. Alright, a certain satellite in circular orbit of radius r remains vertically above a certain point on Earth's equator. So that's like those satellites that are in geosynchronous orbit, right? It takes 24 hours for them to go around. Which of the following expressions correctly gives r in terms of omega, the angular velocity of the Earth's rotation about its axis, m, the mass of the Earth, and g, the universal gravitational constant? Well, if omega is the angular velocity of the Earth about its axis, and this thing is staying above the same point, then it has the same omega. It's like this whole system is kind of like attached. It's not really, but it's like it is. So this has the same omega. And remember that omega is equal to v over r, or that v is equal to omega times r. Okay, so how do we relate these things? Well, with a velocity, I know that velocity is related to some of these things. Velocity of circular orbit is equal to the square root of gm over r. That's a good thing to know. And somewhere earlier in these problems, see if I can find it, I went through the derivation of that, I think. It was in number 14. So if you need a refresher on this and you skip number 14 before, you can go back and watch that video and see where this comes from. So let's see. V is equal to omega r for this satellite. So it looks like I have an equation now with all of the things that I need, but they want it with like r or power of r on one side. So let's see if we can do that. Square both sides. And then multiply the r up here and divide. So it looks like E is our correct answer. I think that's kind of a tricky problem, but once you have the right relationships in place, it's fairly simple. I guess that's true of a lot of things, though. 32. 2 blocks, mass m and 2m, are on a frictionless horizontal surface, as shown above. They're held in place with a compressed spring of negligible mass. Held in place like this, the spring is compressed. If the blocks are released, and the block of mass 2m leaves the spring with a velocity v, the velocity of the center of mass of the system, the center of mass of the system, since momentum is conserved here, there's only forces internal to the system here, this interaction. What's the center of mass before they're released? It's 0. So what's the velocity of the center of mass after they're released? It's 0, because momentum is conserved. It is true that I bet it would be a common wrong answer. If this block has a velocity v, then the momentum of this one would be 2mv this way, and since this one would have to have the same, it would have to have a velocity of 2v in the other direction, and that's true. That would be the initial velocity of this block, but they didn't ask about that. They asked about what's the velocity of the center of mass, and since momentum's conserved, the velocity of the center of mass stays 0. Number 33. Got a 60-gram tennis ball moving at 15 meters per second this way. It rebounds, so the change, I'm just going to notice right here, change in velocity of this thing, it's not 5, it's going 15 this way, and then it goes 10 the other way. That's a change of 25 meters per second that way. So whatever positive or negative, I don't think that's going to matter, but it changes by 25 meters per second that way. To change it by 15 meters per second that way would just stop it, and then we're giving it 10 more that direction. It strikes a tennis racket and rebounds, blah, blah, blah. the ball is in contact, so we also have a time here. So magnitude of the average force. Well, on your equation sheet, there's the impulse momentum. That impulse is equal to the integral force with respect to time, which is equal to change in momentum. But this integral right here, if the force is constant, or if you're just interested in the average force, this integral is just equal to force times time. Again, that's true if you're interested in average force, or if the force is constant, of course that would also be true, equal to delta P. So that means my average force is equal to the change in momentum, which is mass times change in velocity, 0.06. Change in velocity we already talked about here is 25, over the change in time, which is 0.03. They made these numbers nice to do without a calculator. 0.06 over 0.03 is 2, and 2 times 25 is 50. There it is. The impulse momentum theorem. How does the magnitude of the average force exerted by ball on racket compared to the magnitude of the average force racket on ball? Newton's third law, people, equal and opposite. That's like the easiest question in the world. If you're like, oh, well, obviously the racket hits the ball harder than the ball hits the racket. No, wrong. That is not true. There's only one interaction here between the ball and the racket. There's one interaction, only one. So, as experienced by the racket and the ball, same amount of force. So why does the ball go flying and the racket doesn't? Well, mainly because the ball has much less mass. So that same amount of force on the ball causes a much greater acceleration than it does on the racket. All right, last one. Looks like the old kid jumping onto the merry-go-round. Circular platform has a radius r and a rotational inertia I. Platform rotates around a fixed pivot at its center with negligible friction and an initial angular velocity of omega. Child of mass m, represented by that, runs tangentially with speed v and jumps on the outer edge of the platform. When the child is standing on the outer edge of the platform, the new angular velocity is, so this is conservation of angular momentum. And there's different ways you could represent that. I'm just going to say angular momentum initial equals final. So initially, what do we got here? What's got angular momentum? Well, the kid does. We've got like the little L of the kid plus the big L of the merry-go-round, or platform they're calling it. And then final, we have the the angular momentum rather, of the kid plus platform. And at this point, they're stuck together, so it's just one big L there. So the kid, we've got R, M, V, and then sine theta, but the theta is 90 degrees because they're jumping tangentially onto the edge, so I don't need that. Notice there's no sine thetas in there anyway. Plus, the initial angular momentum of the platform is I omega. Get familiar with what these things look like on the formula sheet. And then afterwards, I've got the I final, omega final. So the I changes because you plopped a kid onto the edge of that thing. So there's that, and then I think this is the thing we're trying to solve for. So, I mean, without doing any other work, it's like solving for this. It's going to be this thing over whatever that is. That awfully looks like C, doesn't it? Because there's all that stuff. Now let's just confirm that. So RMV plus I omega is equal to, so what's the new rotational inertia? I've got the I of the platform plus you put a particle, like a kid right there, and just dropping a particle on, that's mr squared for that. So sure enough, that's it. Answer choice C. And that's the end of that test.